So Holger told me there's no rush with the food. The drinks are not going to get warm and the food is not going to get cold. We have enough time to enjoy in all peace and quiet our keynote speaker. It's a huge pleasure and an absolute delight to introduce our keynote speaker, Jon Butterworth. And I will tell you that he is from a completely different field. He is a professor at UCL in London, University College London. He is also at Cern, Large Hadron Collider, that's in Geneva, so a completely different business. Now, Holger asked me when they were setting up this meeting who we could invite as a keynote speaker, and I said, well, Jon Butterworth would be a really good man to invite, because he can tell us something that we don't know anything about, but that is very important for what we do. Now, those of you who know me might not know that my PhD is in physical chemistry. And even less will you probably know that I taught quantum mechanics. So I have a soft spot for those topics. And what I do in my free time is I like reading books, popular science books, particular popular physics books, just to sort of keep in touch with the field. And a few years ago, during summer holidays, I read Jon's book, Smashing Physics, and to be honest, it's a real cracker of a read. That was a pun. Okay, so it's a really great book. And obviously, I've been around a lot of these genome projects and human genome and IHEC and ICGC and all of these things. And I know that me and many of my colleague scientists sort of look over the fence and go, gee, these physics guys, they really have it sorted. They do big projects. They manage to get huge amounts of funding. They do that really well. And they manage to write papers with 1,000 authors. And they agree on who's the first author. It's very easy. It's the guy who has a name that starts with 2 A's and a B, obviously. So they go with alphabetical order. So I think we have an awful lot to learn from this community, and I think we can learn to sort of how we can organize our projects and so on. So I'm really looking forward to what you're going to tell us, and I thank you ever so much that you sort of accepted Holger's invitation. I had to push him to call you at some point. Okay.
Thank you very much.
Okay.
So yeah, well, thank you very much. As you said, it took a long time to get through the spam filter, I have to say, the invitation. There are so many conferences that I get invited to that are not my field, but it's a real pleasure to be here for this one. I've spent the day, I've been here since lunchtime, listening to the talks and trying to work out where we have problems in common and where we have completely different scenarios. I apologize if I overgeneralize on occasion and talk about things that are just not relevant to your area. But I think there are certain commonalities of doing big collaborative science that I hope that are useful, at least, or interesting to you. And because I'm a physicist, I'm going to spend about half the talk just talking about particle physics, because it's cool. But there may be nothing in common there, but I hope that's acceptable. It's the first time I've been between a lot of hungry cell biologists and dinner, so I won't go on too long. Okay, so this is the star of the show. This is the Cern Large Hadron Collider. This is the view you get as you approach Geneva Airport, which is here over the Jura Mountains. This is Mont Blanc on the horizon, Lake Geneva here, and the fountain is somewhere in there. I mean, also, of course, I lie. You don't actually get this view. They wouldn't let us paint the yellow circle on the fields, but it's marking the path of the Large Hadron Collider, which is a tunnel underground, on average about 100 meters underground, which contains, it's basically stuffed full of superconducting magnets to steer and accelerate and bring into collision the two highest energy beams of particles that we've ever created and controlled in a laboratory. They're both beams of protons, they're counter-circulating, and they're brought into head-on collision at 4 points. LHCb, Atlas, which I guess is connected with why I sprung to mind about this meeting, which is my experiment. Alice and CMS. And over the next 20 minutes or so, I'll try and tell you why on earth we're doing this and something about how we did it. The how starts with politics, I guess. It's the organization behind this, which is Cern, the Centre Européen Recherche Nucléaire. It's a bilingual lab, as you can probably tell by my French accent. You don't need to speak French to work there, but it helps. And it was founded, these are the member states, current member states coloured in blue. The most recent additions, actually very recently, was Serbia and Romania. And in fact, I just got an email today that Croatia has joined as an associate member on the path to full membership. In fact, Yugoslavia was one of the founding members of Cern, but then, of course, when it split, it no longer kept up that membership and now is rejoining piecemeal. It was founded in 1954. Interesting from a UK point of view, we were one of the founder members, and one of the last things Winston Churchill did as Prime Minister was sign the deed saying, yes, it will be in Geneva and it will be here. And it was a very deliberate political act. It was to try and, the leadership in fundamental physics had very definitely moved primarily to the United States with the Los Alamos project and its various follow-ups, and also to the Soviet Union. And Europe was a mess in the 50s, of course, and it was really deliberately non-military, not driven by economic applications, but just to try and re-establish, if you think about the early 20th century with Schrödinger and Heisenberg and Einstein and Dirac and everyone building quantum mechanics, it was all in Europe, and that had all gone. Even Fermi had gone to the United States, and so had Einstein. It was a deliberate attempt to try and build some of that collaborative spirit back. It took a long time. It had a small budget at the beginning. It took a long time. The national labs were competing with it to some extent. One of the great, but it was stable, and it had a cumulative effect of investment and integration and infrastructure that was built up there, and knowledge of the people that were there, to the extent that now it's essentially the global centre for this. So although, again, here you have the member states coloured in the darkest colour, we have a lot of associate member states who don't pay the full whack. The member states pay a strictly GDP proportional amount to keep the laboratory running, which works out roughly €2 per taxpayer per year, which adds up to, if I got my numbers right, it adds up to about just over €1 billion a year, or €1 billion a year, possibly. So, but the associate members also contribute, but less. There are ones that are joining, which will become full members, and then the observers in other states, so powerful countries with their own major particle physics initiatives, such as Japan and the United States, they participate in the science program at Cern, but they're not members of the laboratory, and they have observer status usually because of that. And even the ones that are just labelled other states, they're all coloured in because they have scientists working at Cern and they're collaborators on some of our projects. And I'll try and explain something about how that works organisationally. One of the key things in that is the distinction then, actually it's key scientifically, but it's also key politically actually, is the distinction between the laboratory, which provides the accelerator and the beams, and the experiments, which are the detectors, which detect what happens when the beams collide. Because the scientific papers and things are published by the collaborations that run the experiments. And this is the one where there are 3,000 of us on Atlas that help build this thing and now run it. And we share all the data from this experiment amongst ourselves. The other guys on the other end of the ring, CMS, we don't have anything to do with them. And we don't even drink coffee with them. Okay, we drink coffee with them. But in fact, some of us are married to some of them. But we're not scientifically independent. We have statistically independent data sets. We have different technologies in the detector, completely different funding streams and things. So the idea is to keep some independence despite the common dependency on the beam. And the lab, the beam itself is paid for from the lab subscriptions from the member states and associates. The experiments are funded separately. You bid to the National Funding Agency to go and get money to build some part of it, and then it all comes together like some big high-tech jigsaw. The UK built this is a silicon semiconductor detector in the middle, close to the beamline. We built some of that in the Rutherford lab in the United Kingdom, with lots of universities, including UCL, collaborating on that, and various other bits of the readout electronics. The other bits of the detector were built all around Europe, but not just around Europe, around the world now. So the United States and Japan in particular, and Russia, made major contributions to the construction of this experiment. And our full members, although they're not full members of the lab, they are full members of the experiment, and they contribute to the running costs and they have full scientific access to all the data from the experiment, and a say in what the priorities are and how it works. So this is the engineering drawing of it. The beams going through here, and they collide in the center. you see this kind of concentric cylindrical structure with each is a different layer of technology telling us something about the particles that are produced. So I'll show you an image from this in a minute, but when the protons collide, many particles are produced, and we want to characterize them, we want to see what their energy is, we want to see where they came from, where they're going, what kind of particle they are if possible. The only other thing I'll say about this, given the shortness of time, is that it's quite large. So these are standard European-sized people here. It's about 50 meters long. And unfortunately, you don't get this view of it now. It's underground. This is a picture, quite a famous picture from 2005 now, in fact. Time flies. While it was being constructed. I give talks in schools quite often, and this was very often on the wall of the physics lab, or even in primary schools sometimes on the wall of the classroom. This is while it was being built. So these orange things here, stripy things, are these toroidal magnets here, which are part of the muon detection system. And the whole middle bit hasn't been put in yet. This guy's got to get out of the way before it goes in. He's one of the people building it. You can visit Cern now, and you can go underground and you can see it, because we're actually on a maintenance shutdown at the moment for a year and for another nearly 2 years before we have beam again. And it's worth doing if you can, but Atlas is actually not the most impressive one because it's so big it fills the whole hole, so you don't get a sense of the size anymore. You sort of see the side of one of these wheels if you go in there. But the other experiments, which are actually not quite as big, actually look bigger and more impressive. And it's well worth a trip. If you've got a few hours to kill at Geneva Airport, we're only 20 minutes away on the tram. It's worth having a look. This is one of the pictures you take from these experiments, or one of the ways obviously you represent this. It's a massive amount of digitized data, and we can represent it in all kinds of different ways. This is one of the event displays that you'll see on the control room wall if you go into and look at Atlas. That you've got to imagine that this spot here is the collision point. One of the beams came from the projector, one comes from behind the screen. They collide at the red dot. Most of the protons come in bunches, about a few centimeters long, and there's a bunch passes through each other every 25 nanoseconds. Okay, and most of the protons miss and go all the way around the ring and have another go and keep going like that. So when it's running, we run 24/7, and a beam fill will last for several hours. Most of the grayed out stuff here is uninteresting tracks. The higher momentum ones, which are not bent so much by the magnetic field, and in this case are muons, because they punch right through the detector and registering the muon detectors at the edge, are the ones we would be interested in this event. But you can see here from a zoom in on the same event on the longitudinal cross-section, so this is the side-on view of the same event. You see that there's more than one source of particles here, and that's this bunch of protons. In this case, about 15 different pairs of protons collided, and only one of them produced the particles of interest. The way we were running just before we shut down, this would be more like 50 or 60 pairs of protons would collide, because we obviously want to squeeze the bunches down and get as much data as we can. The price we pay for that is noise, and that we get more collisions in a single time window. Probably the other thing to note, so that's a data analysis challenge. One of the other things to note about this is that the speed of light is about 30 centimeters per nanosecond. None of these particles are traveling faster than the speed of light. Most of them are traveling about the speed of light. But the detector is nearly 50 meters long, so there's no way in 25 nanoseconds that these particles can have exited the detector. So we have this huge asynchronous data deluge basically coming at us while we're running. That is processed, some of it actually on the detector in high-speed ASICs, application-specific integrated circuits, and FPGAs, field programmable gate arrays. Try not to blind you with algorithms, with acronyms, but I'm sure you use a lot of these things yourselves. And then goes into a big, basically an office block full of Intel boxes that try and put the event together. Every bit of data has to be time-stamped, so you can work out which 25 nanosecond time window this bit of information came from, even if it arrived much later than you've already had another 100 bunches through in between. And then it gets found out all around the world on a computing grid. So there are tier 1 sensors, we call them. A cloud is probably what we'd call it these days. So in the UK, there's one at the Rutherford lab, but every major collaborating country has at least one of those, and then eventually ends up in the universities on laptops, and we write papers with it. And that's kind of how it works. And although people all around the world have built bits of this detector, it's not separate detectors. It's not like if you're working at a light source where you go, you book some beam time, you turn up with your postdocs and your students, you collect the data and you with your samples and stuff, and then you go home. It's not like that. We all have access to all the data, and all our bits of kit have to work completely together, and we share all the data amongst the 3,000 or so people on the experiment. This is our atlas, our periodic table. I showed you the periodic table of the human body earlier. We haven't see a picture of the actual periodic table, but this is you can build the whole periodic table from this. If you've got 2 up quarks and a down quark, you have a proton. 2 down quarks and an up quark, you have a neutron. So that's all the atomic nuclei you can build from that. And then if you add in the electrons, you've got everything. So it's all there. All your cells are made of this, basically. It's not entitled, so I don't know what all the fuss is about, really. For reasons we don't fully understand, I mean, there are these neutrinos, which we do understand why they have to be there. They're produced in beta decay, and they're critical for the fusion reactions in the sun. For instance, there's lots of them produced by the sun. But it's copied again 3 times, so this is a charm and a strange top and the bottom. These all decay very quickly back into these guys, so all the stable matter in the universe seems to be made of this. But these exist, and they exist briefly, and they're created at the LHC, they're created in cosmic ray interactions in the upper atmosphere. And they interact via these forces, so the photon is what's coming out of my laser, it's the force carrier of the electromagnetic interaction, the gluon, and then the carriers of the weak force. And in the background is this mysterious field drawn in there, which I'll come back to right at the end of the talk, which is the only way we could build a mathematically consistent theory where these supposedly infinitely small constituents of matter have mass. And that's a very conceptually difficult thing to grasp. It's also mathematically difficult to write down a theory that makes any kind of sense that has that feature. And the only way we managed to do it was introducing this background field in the universe, which is non-zero everywhere. And by interacting with that, they get mass. And I'll come back to that in a minute. I want to say something about the organization. So this is our web page. I think it's obligatory at this point to point out that the web was invented just downstairs from my office by Tim Berners-Lee and his collaborators at Cern. I don't know, we've probably milked that one enough, but we'll see. It's one of the bit of us getting funding and things. It's definitely something you have to mention. But anyway, this is the collaboration web page. Nothing particularly exciting about that, except that it reminds you that this apparatus, when it comes to big distributed science collaborations, having a central apparatus, i.e. the beam, and then in this case the detector, and having to run it, so operations, systems upgrades, trigger is the online data selection, for instance, and then actually our publications. It's a curse and a blessing, right? I mean, it takes a lot of work and a lot of money to make it work, and it means we have to spend a lot of time traveling to Cern and things. On the other hand, it binds the collaboration together. There's nowhere else you can go. If you want to work, you can't take your toys and go play somewhere else. You've got to work on one of these if you want to do this kind of physics. And that, I think, is why particle physics sort of led the way in becoming big science. And our astrophysics colleagues have clearly followed us now with the big, the LIGO detector and the big telescopes, where you have to, if you want access to that cutting-edge data, you have to work together because you can't afford your own. And if you're going to argue with each other and refuse to work with each other, then one of you will have to leave the collaboration. There's nowhere else to go and do this science. So that's kind of, as I say, it's a curse and a blessing at some level. The meetings is definitely part of the curse. This is this week's meetings. Most of my colleagues are in Berlin at the moment. We have a collaboration meeting in Berlin going on. And in fact, I spent the part of the breakout session listening on a teleconference to a discussion, an argument about publication policy and open data and how we allocate conference talks and really tedious stuff like that, which I'm sure are all problems you're going to have to worry about in a big collaboration like this as well. It's very difficult to work your way through this, and while I think there may be things that other sciences can learn from the way we collaborate, I think it goes the other way too. I think we're behind when it comes to open data, for instance. We're very good at sharing data amongst ourselves, but if you look at what astrophysics is doing, they do that, and then after a certain number of years, it all goes out in standardized formats to the whole community, and we don't do that at the moment. In fact, that was one of the things we were arguing about. We will do that soon. A lot of people are very reluctant to do it, and a lot of people really don't get the concept of open data within our collaboration. So although we're completely open within our 3,000 people, and we kind of led the way in being open source about our code and reproducible about our analyses, it was all within this ring-fenced collaboration. And going beyond the collaboration is controversial, I would say, and it's not something that we're leading the way in. I think we have things to learn there. Collaboration tools are actually quite sophisticated. This Indico is also an open source meeting management thing, which is tested brutally all the time, and was developed at Cern a few years ago, and is now actually being used by the United Nations to run their meetings. And you might want to consider it. We don't make money out of it, so I'm not marketing it here. But there are some really practical things like that save a lot of time, just for slide upload and linking to video conferences and timetabling and registrations and things. It's kind of handy. Anyway, this is a kind of the obligatory org chart, organization diagram. I guess the main thing is to say there's a lot of, these are the people who really run the experiment day to day. They're usually 2-year rotating positions. Some of them have to be CERN staff, so they stay there for longer, but a lot of these are people from universities who get seconded to CERN for a little while, or from national labs and get seconded to CERN for a while. We have a spokesperson who's the boss. This confuses the heck out of the media quite often. They think the spokesperson is just whoever gets shoved out in front of the gates to apologise. But actually, the spokesperson is elected and is the boss. The collaboration board is the kind of, I guess what's the word I'm looking for? It's the non-executive directors or something. There's one vote per institute. In the end, it's a decision-making body, but you hope it doesn't have to make any controversial decisions mostly. It meets 3 times a year. It's meeting tomorrow in Berlin to argue about open data. Actually, they postponed the decision, so that was good. We'll see. I'm glad they did, actually. And we have a plenary meeting, and people get appointed to this by various degrees of transparency and in election and endorsement. And it's not a stable or completely solved problem forever. It requires, personalities enter into it. You've got to allow new people in. You've got to stop someone dominating one area forever. On the other hand, you have to take expertise into account, and also geography and diversity and ethnicity and all those kind of things. It's a management challenge, I would say. This is the map I showed you before, the map of CERN members and collaborators. This is Atlas. Everyone coloured in here is a full member of Atlas. There's no intermediate membership states or anything. So you see it's truly global. We have the big membership in South America, some from Africa, Australia, and across Asia, including China and Japan. And that was where the institutes are. This is where the people come from. And there's clearly a big mix in that, and it's even more diverse if you look at that. If you look at people's nationalities, this is our. I was going to say Nobel Prize winning paper, but it didn't win the Nobel Prize for us. It won it for Peter Higgs and Robert Brout. But nevertheless, it was the Higgs discovery paper, and I'm going to finish up by just explaining a bit, by showing you that data and explaining what it meant. If I've got time, right? Yeah. So this is the author. I was chair of the physics department in UCL until the end of last year. And one of the things I really liked was being invited into meetings where we were discussing metrics and appointments and how do we tell whether anyone's any good and what have they done. And it was always particle physics is the problem, because we've all got thousands of papers with thousands of authors, and what do we actually do about that? It doesn't make, hundreds of papers with thousands of authors. I'm not sure it's a solved problem. I know why it's there, because if we started arguing about there you go. We don't have an AAB. We got an AAD. If we had to argue about the ordering of the author list or the membership of the author list every time, we'd probably have published one paper by now, if that. Given that we postponed our discussion from the collaboration board already today, I think we might not even have written one. So this goes up to BE. Okay. So I'm Butterworth. I'm not even on there. This is page 2. There I am. So we do confuse the heck out of university, ref panels and God knows what, because they don't really know how to make this. Of course, it's a bit of a fiction, and I'm not sure this is in the end a long-term solution to our way of working. Because in reality, a paper is always written by a much smaller group. Maximum, the Higgs paper, maybe there were 100 people really directly involved in it, and that's going to be the biggest it ever gets. In fact, there were what? That's a lot. Still a lot, right? Yeah. But I mean, now you can divvy up the tasks, and it's a lot. There's 3,000 on the paper, so it's a small fraction of the paper. But yeah, you can divide up the tasks, and some people go and work on the background calibrations, and some people go and work. So you can divide that. Usually, even then, those tasks will be divided into groups of half a dozen, even, and down at that level. Some of the papers are essentially written by a PhD student and their supervisor, and that's that. I mean, they're on the less high-profile ones. Yeah, they've all got these authors on. So when you write, and the collaboration at some level has sign-off on all of them. So I'm not sure that's the most efficient way of doing things. I've argued in the past that we have an opt-in author list, that everyone has the right to sign, but you don't have to sign if you haven't had time to read the paper. That would make me feel a lot better about some of the papers that are out there in my name that I haven't even read. I don't like that situation, frankly. I'm not sure it's ethically correct, in fact. But I know why it happens. It's because we don't want to get into this argument because our experiment works. It takes a lot to make it function, and at the moment we're producing the results. So it's a kind of, it didn't broke, don't fix it. I'm not sure it's not broke, actually, but there we are. Okay, so this is another picture. I'm going to just finish up now with the Higgs, basically. This is another representation of one of the collision events. So again, this is a slice through that cylinder that you saw with one of the beams coming from the projector, one from behind the screen, colliding here. The protons smash each other up, so there's all kinds of particles produced from that. The interesting ones in this are these two yellow blobs. They don't have charged particle tracks pointing to them. They're actually photons. They don't look terribly impressive there, but if you look at a histogram of the energy, they stand out above the noise by miles, so they're clearly significant. I talked about the business of introducing this background energy field in the universe, which has a vacuum expectation value. So if you want to remove it from a bit of space, you have to put energy in. Most of the fields, like electromagnetic field, the lowest energy vacuum will have no electromagnetic field in it, but it will have this Higgs field in it. And it has to be like that because it's by interacting with that particles acquire mass, so it has to be everywhere. That's a nice mathematical dodge, but it's a big thing you've done there, just filled the whole universe with a field you just made up in order to explain mass. You would like a phenomenological evidence for that, something a bit more. I mean, a field is a tricky thing to pin down. I mean, you think, so for instance, take an example, the air in the room you can think of it as a pressure field, okay? Every point in the room has a pressure. That's a field of numbers you could write down. One way of detecting the presence of that pressure field in this room is the fact that you can hear me. So if there was no air in this room, you wouldn't be paying attention for a start, but you also wouldn't be able to hear me even if you were, because there's nothing for the sound to propagate through. So what you're hearing is pressure waves. That's basically a very good analogy of how you would work out that this background energy field is there in the universe. Just hit it really hard and see if it wobbles, see if you get a wave. Now, it's a quantum field, so those wobbles will be quantum excitations, which is essentially what particles are. And so the quantum excitation of that background energy field is what we call the Higgs boson. So we would like to see whether this thing exists. If the field is there and has the properties needed in order to give things mass, it must be excitable. You must be able to hit it and make these wobbles in it. Now, those particles, the Higgs boson, will decay extremely quickly to standard model particles. It's not something you can get them all in a jar and take them to Stockholm. They will just fly apart. But they will fly apart to things we can see, and one of the things they'll fly apart to is pairs of photons. So you can do a bit of relativistic kinematics and say, if these photons came from a particle, what was its mass? I've measured the energy and the angle of the photons, so I can calculate that. Okay, and then I just count the pairs of photons. This is where all this technology, all these meetings, all these things boil down to a really nice final punchline, I hope. You can count the pairs of photons. You can calculate that hypothetical mass for each of them. There are lots of ways photons can be produced, so there'll be a continuum background of noise, basically. But if there's a new particle in there, there'll be a concentration of masses around that particle, and essentially there'll be a bump in your distribution. So this is it. There's the date up here when we were taking the data. This is the number of pairs of photons. This is that calculation, the mass in the middle. You see the noise, you see the error bars, the points of the error bars. The blue is a smooth background fit. And the error bars, statistical errors are shrinking as we collect more and more data. All the bumps go away, except for one of them, which is that one. And that's it. That's the Higgs boson. If you know what's going, think about what's happening there. You're actually seeing this theory was predicted from mathematical consistency of quantum field theory and gauge theories in the early 60s, right? It's a completely new thing in nature. It's not like just another quark or just another force carrier. It's a scalar boson that is the evidence for this background field in the universe. There's nothing else like it in the standard model. It's a complete bolt-on that we were led to by our mathematical ideas about the way the universe works. The fact that I didn't believe it would show up. I thought this was fantasy land. I thought it was worth finding out, but I honestly didn't think it would show up, but it did. Possibly another important lesson from this is that all the data I've shown you is from my own experiment. There's another experiment, CMS, which is diametrically opposite on the ring. When we found our bumps, I was actually, at the time, I was leading the UK part of Atlas, and I saw the talk by our then spokesperson, Fabiola Gianotti, who's now the Director General of Cern. I saw her practice talk the night before of the seminar she was going to give announcing the discovery in Geneva, and then I had to go back to London because there was a press conference and the science minister was there and all the journalists who couldn't blag a trip to Geneva were there, so I had to be there. And I was really annoyed about that because although I'd seen our data, I hadn't seen the CMS data. And although if you'd have asked me, I'd have said, absolutely, we're right, absolutely believe our data. We have a bump, it is the Higgs boson, we have a new particle there. I really wanted to see the CMS data. So Jim Verdi, who was at Imperial, was also nicely diametrically across the circle line in London, actually, which is the same length in kilometers as the LHC. And also yellow, which you see on the picture at the beginning, was yellow. Anyway, he was there, and he hadn't seen our data either. And so the whole thing was going to kick off about 6 in the morning. And at 5:30, we were there, and we secretly showed each other the data from our own respective experiments. And it really surprised me because I got this kind of knock in the stomach. But when I didn't believe our data. It turns out I thought I did, but my head believed it, my stomach didn't. So when I saw that they had the same damn bump in the same place, and I just got the chills because I thought this is really, we've seen something real and new now. Now I thought that already, but it turns out I needed to see the CMS data. Okay, so that's the story of the Higgs. We were still running, we're still taking data. And in this animation, you can see why. Let's just make it run one more time. So as we collect more data, we're shrinking the errors. It's like rolling a dice. You know, how fair is it? 6 rolls tells you nothing. 6 million, you should work something out. Every time we shrink this down, we're actually, in fact, getting a better resolution look at the heart of matter. And we're studying the properties of this Higgs. We'll see, is it fundamental? Has it got constituent particles? We don't fully know. As we get more precise data, we're working some of these things out. What we are really now is in exploratory mode. And I wrote another book. This is about the map of the invisible. This is the follow-up. And the privilege of writing this book is I got a very nice artist, very good artist, Chris Wormel, to draw the nonsense that's in my head. So it turns out this is actually the way I think of particle physics. We have this landscape that we understand. The electron gives you access to atomic physics. As you go up in energy, which is kind of further east, we see the nuclei, we see the hadrons, we see that actually they're made of quarks. We have the source of all the interactions here. We have the Higgs far out at the highest energies here. And we're now, this is the LHC exploring this eastward sea. There were many theorists that told us we'll find the Higgs for sure. See this ridge of mountains? That's the electroweak energy breaking scale, symmetry breaking scale, which is the energy the LHC was designed to go over. And it did. They said, we'll find the Higgs. They said, and when you find the Higgs, there'll be another island right here called supersymmetry, and it's not there. Okay, or there'll be something else there, and there's nothing so far, actually. All we see out to the east so far is ocean. We're studying this bit of land much more carefully. We're still learning things, actually, about the whole deal. But we're sailing eastward now. Every time we collect more data, it's a few miles further east. We know there's stuff out there. We know that, for instance, you can't understand the motions of galaxies without either postulating a different theory of gravity than Einstein has, which we haven't managed to do. Turns out Einstein was quite clever. Or postulating something called dark matter, which is 80% of the mass of the universe. That's not a small correction. It's kind of annoying if you're trying to understand the fundamental constituents of nature to think you might have missed 80% of them. Also, we don't understand even the matter that there is there. Antimatter is kind of workaday. We produce it all the time. But every time we produce antimatter, we produce an equal amount of matter, and every time we get rid of antimatter, we annihilate an equal amount of matter. If that's what the physical laws say. If that happened in the Big Bang, where's all the antimatter gone? All the matter around us should have an equal amount of antimatter somewhere. We don't know. There's obviously a breaking of that symmetry somewhere. We don't know. It might be hidden somewhere here. It might be some theory further out east. It might be within reach of the Large Hadron Collider. It might not. It might require something further to do that. And in fact, right now, there's a European strategy process going on. We had a big meeting in Granada. We're going to have a smaller drafting session in Bad Honnef in Germany in January, where we will kind of starve each other to death and agree with no one gets to eat until we've agreed what our strategy is, basically. It's the only way we'll ever agree. To try and work out what the options are for exploring further in this direction. So watch this space and we'll see what happens. But I hope I've given you a flavour of what the endeavour is like and what it's for at some level anyway. And I'm happy to take questions. Thank you.
Wonderful, thanks ever so much. Does anyone want to ask any questions about physics? Okay, you're all scared.
Yes, we have one, yes.
So I actually entered this Slack for a while, and there's a Barber experiment looking at CP violation.
Yep.
And I think people talking about CP violation and dark matter, so that would be the antimatter bias and then dark matter involvement. I haven't gotten a clear view of that. I don't know if anyone else here is interested in that, but it goes to the fundamental fabric of the universe, right? So like
Yes.
Is anyone at Cern talking about that, or?
Yes, no, that's one of the big issues at the moment. In fact, the LHCb experiment, which I didn't talk about, was designed specifically to follow up from Babar at Stanford. And there's the Bell 2 experiment now in Japan, which is also following up on those results. There's room in the standard model for a little bit of asymmetry between matter and antimatter, but it doesn't seem to be big enough to, and it's there, but it's not big enough to explain the gross discrepancy we see. In fact, Babar established that that asymmetry is consistent with our standard model. There's also room for some of that in the neutrino sector, and there's an experiment in Fermilab now, which is and another one in Japan, which are looking whether in neutrinos there's a similar amount of matter-antimatter asymmetry. Again, that might not be enough to explain the discrepancy, although we don't know yet. So this is very much a live question, and you're absolutely right that our simple dark matter model, if you're missing 80% of the universe, couldn't some of that be the antimatter? And that's absolutely, it might well be. There are dark matter models where the kind of Occam's razor approach is, let's just say there's one kind of dark matter particle, in which case that isn't going to work. But that's just the simplest starting point, and there could be a whole dark sector of different particles out there, and we're just seeing a small correction from that. So yeah, it's very much what's out there on the east. That's very much live. They're very much live questions, right at the forefront of what we're trying to do, in fact, now.
Further questions?
I was wondering if you could say a little bit more on what you think the next generation of accelerators will be, and what's the increase in energy scale?
Yeah, sure. So there's before I do, the first thing I'll say is that accelerators are not the only way. So there are neutrino experiments that I just mentioned that are going to do some groundbreaking stuff, and there are also some precision. Quantum metrology has come such a long way that we might be able to get access, by making super precise measurements, we might be able to get access to some of this new stuff. But focusing on the energy frontier, which is kind of the cleanest and frontier of working this out, basically energy gets you resolution, and that's the bottom line. There are two options on the table, really. One is to collide electrons again, which is what actually was done in the LHC tunnel before we put the LHC in there, before we put protons in. You can't really get them to very high energies anymore in a ring because of synchrotron radiation. You're just losing too much energy. But you can get it if you build a bigger ring. There's a proposal for a 100-kilometer tunnel, or there's also proposals for linear machines with electrons that could certainly get you to a point where you can resonantly or sort of resonantly produce the Higgs, and you can make much more precise measurements of the Higgs by maybe a factor of 5 more precise than we can. But in particular, one thing you could do is measure the width of the Higgs, so everything it decays to inclusively. That's important, and we'd love to do that. But that doesn't really advance the energy frontier. That's really studying what we know more closely. To study the energy frontier, either you take the electrons in a much longer linear machine and you go that way. There's a proposal called CLIC at Cern to do that, and there's a proposal in Japan called the International Linear Collider to do that. Or you go back to protons, and then you could get an order of magnitude further in that. The problem is we don't know whether an order of magnitude is enough. We don't have a thing to shoot at. So with the Higgs, we had a thing to shoot at. So you could say we might end up doing an order of magnitude and find that everything checks out with the standard model. Now that would tell us something profound about the universe. It would tell us the standard model is kind of isolated, which is not something we thought was. It kind of violates naturalness. It shouldn't happen like that. It would change our ideas about physics, but it's not, it's not discovering a new particle at some level. So that's the discussion that's going on right now. And there are also further away, there are new accelerator technologies being developed, and colliding muons is another possibility people are discussing. But the two main ones are what we call a Higgs factory with electrons, or going as far as you can, going for broke with protons to just see if there's anything out in that ocean there within reach.
Thank you. What is very striking about your community, the particle physics community, is I think your ambition. And by that I mean both in terms of the difficulty of the scientific questions you're trying to answer, essentially what seems unanswerable. And secondly, your ability to acquire unimaginable resources in order to be able to address that. With those two in mind, what would your advice be for the Human Cell Atlas community? How do we actually raise our game, if you like, to first of all be more ambitious in terms of the questions we ask, but then how do we actually go about creating the resources and infrastructure and the collaboration to address those?
Okay. First, I would say, I believe, honestly, you have a more difficult problem than we do in terms of the science, actually. You have a more complex system, right? So a lot of the complexity of our machinery is designed to make the physics as simple as possible, as clean as possible, right? It's the resolution. So I have only my 6 quarks and 6 leptons. We've got a lot more cells than that, okay? So and a lot more noise, a lot more variability. So it's different in that sense. But I think that the thing that's worked in particle physics in terms of funding is with two things. You need an ambitious question that you're going to address that can fire the imagination. And primarily, it's firing the imagination of your fellow physicists, not of the general public. If your physicists are all excited, the general public will generally follow, so will the politicians. But the beautiful thing about the Higgs discovery was the media spent so long pointing microphones at the spokesperson and the big professors, but then going to the PhD students to find out if this was all hype. And every PhD student was more excited than the professor. So there was everyone was on message without even trying because it was real. Okay, you need that at some level. So that's the ambition. You need the ambition and the excitement. But what's less well known is that there's a hinterland. So the Higgs is one paper. We've published about nearly 1,000 papers now. And so everyone is really interested in one of those. The most cited papers after the Higgs, which literally have thousands of citations as well, are about the heavy ion physics program there, which I didn't even mention. But that's studying hot, dense QCD, quarks and gluons. So you have a diversity of physics that follows on. You don't build a machine just or build a collaboration just to get one number or solve one problem. You need an ambitious headline or two. But you also need that hinterland because that's how you get a whole big community involved. And you say our resources are unimaginable, but they're not that big if you consider how many people are actually working on it. And it's that hinterland that brings in a big community. They say, well, I may not care that much about the Higgs, but I could do this with that machine as well. And then they come and join in. And that's how you build the resources and you build the momentum to get the thing going. So it's those two things, an ambitious headline, but a big hinterland as well. And allow innovation and allow people to have academic freedom and curiosity in that hinterland, but also keep your eye on the main prize as well.
I mean, one difference is clearly this curse and the blessing you mentioned, right? There's one machine and everybody has to gather around it because that's, of course, not the case, right? I mean, here we don't have one machine that we built. And so do you can think of other projects in physics where there also was not one machine, so you could go somewhere else, but where collaborative efforts kind of made a difference? Or can you comment on how these structures might be different? Because I think that's a major
I
change,
understand.
difference.
I mean, probably the best analogy is, the guys who got the Nobel Prize this week, actually, on exoplanet discovery. That was clearly very dependent on technology, and there are multiple techniques for discovering exoplanets and analysing them. And there were not a huge number, so there had to be still quite big groups, the order 100 people or so, but there was more than one. So if you fell out with one, you could go to the other. But I think now the astrophysicists are generally building towards bigger collaborations as well, because they want the best telescope or the best satellite they can imagine, and that means getting everyone to work on it. But they've gone through this evolution stage there for sure, where the idea was a bit out there and the technology was not that expensive. It was more about some of them were just making use of serendipitously of things that already existed. So I'd say there it made a difference, that being able to collaborate on what were big groups. I mean, they're still big groups, but they're just not as monolithic as Cern. So yeah, that's one example that springs to mind, probably just because of the topicality of the fact that they won the prize this week. I know that people are. I mentioned quantum sensors as a big initiative in the UK now to try and collaborate on using quantum sensing to do things like fundamental physics measurements, so gravitational waves measurements on a desktop maybe with very large-scale coherent systems, which are a new thing, which have to a large extent come out of quantum computing research. And the research councils are trying to pull that together and say, let's not just spread all our efforts everywhere, let's try and coordinate, but there's no monolithic central facility there. Those things work sometimes, not other times. It probably depends who's involved and how smart the research council is and how focused it is, I guess. I mean, Wellcome seems to be quite good at laying down these things at some level, but from the outside at least. But yeah.
So, aside from their scientific curiosity and ability to do what they want in the context of resources that they need, what's the main currency for people for success?
In this?
Yeah, for a student, for a postdoc. And where do things not work so well for them? Because, in every system, and definitely in the academic system, it doesn't matter. We have a way of doing authorships, and computer science does it differently, and so on. Nothing is perfect.
No, exactly. No, we have problems with this, actually. It's a big, I believe, a problem that people whose careers are established maybe haven't realized how big a problem it is for the generation coming through, in fact. The currency is how many papers did you really work on and make a difference to, and what kind of story can you tell for what you did for that paper, and who will back that up as a reference, because obviously you could say whatever you like, but you get senior references from the collaboration, from your supervisor and things that will say, yes, this person really did make a difference. That is also recognized by the collaboration in terms of awarding keynote talks and conferences and things. If you get asked to go and give significant talks on representing the whole collaboration, that's a marker. And there's an org chart there, and if you lead a group there, then that's something that's unarguable and is on your CV. Of course, having the position isn't what counts. It's what did you do with the position when you got it, but it still matters. That's part of the currency. The flip side of that, and I do think that kind of works at some level, but what I worry is that we mitigate against innovation. My big worry about our field at the moment is that the best way of getting a paper out is do what the person before did, because the other 3,000 people have got to review it. And if you've done something new, you might get held up 3 months by an honest review of some new thing that people want to make sure it's right. And if it's right, you get all the credit for it. But if that 3 months means your job application or your grant proposal has crashed and burned in the meantime, that's very bad news. And I think we haven't solved that one yet. I think that worries me that in the long term we will end up doing more of the same, and we've got to break out of that somehow.
Are you also, just as a follow-up, are you also worried about people being beholden to references, which is a general problem for academic communities?
Yeah.
Or is the large, 33,000 people or whatever it is kind of polices itself for at least some level of honesty?
My experience, and this is partly actually based on life at UCL as well, is that that's not such a big problem, because there are multiple people you can go for a reference. And so And you're actually much less dependent on your supervisor even, because you can find your intellectual home within this big collaboration. It's very different from being in X's lab and everyone has to be on the right side of X, otherwise they won't get a reference. It's not like that. There's no one person controls it. And within the collaboration, if you find someone completely impossible to work for or with, you can go and find someone else within the collaboration and it will work out. And in fact, that happened to me as a PhD student. So. That was in Hamburg, not at Cern. That was at Daisy, actually.
So, responding to some of the things you told Aviv, to things that came up, if it all depends on references and being acknowledged for what you did, how do more shy and more quiet people fare? Because I know that in some communities, some of these people aren't loud enough and other people pick up on what they did and sort of grab it from themselves. And do you have that and how do you handle that? And the second question is, I'm really struck by the innovation comment that you make, which I think is a general problem in science. So do you have an idea on how to break that?
Yeah. So on the first one, this is a general feature of any sociology, and I think I'm not saying we've solved it. However, we do have metrics. So because we're a big collaboration, and we do keep records of who's done what, actually, and we do have formal systems for saying these are the main authors, you have been appointed principal editor for this paper, these are the things you will do. That will be on record. So even if if someone else tries to claim all the credit for it, they might get some way, but if someone goes and checks the database, they may smell a rat at some point, and there will be people there who have enormous amounts of things they've done, which maybe they don't get credit for unless they speak up. But if someone says, at some point they'll have to put themselves forward, I guess, or their supervisor will, or someone. But it will be on record, so it's not just, you can't just talk a good talk, you've got to have done it as well. But I'm not saying it's perfect. There's still an effect, clearly. And some people give good talks and some people give terrible talks, and it doesn't necessarily correlate with whether they did the work or whether they're the best scientist in the end either. So that's, I guess, everywhere. And I think the only thing I would say to that is we do have formal internal recognition systems, so you can't just blag it forever. You have to have actually got some contribution behind you. On the innovation one, I don't know. We are moving towards open data, and one thing I think that's part of the solution, because I think once you have open data, you can go and do a little paper demonstrating a technique on the open data without having to get the whole collaboration to sign off on it. And then if the collaboration looks at it and goes, that's a good idea, and then uses it, then you've clicked, that's golden, right? Then you've really done it. You've got the innovation out there quickly. You can have the high risk, high reward thing, because but you don't have to spend years on it. You can get the idea out in the open and publish it, rather than having it squashed on internal review. And you can have it within the 3 months you needed. And if the people who are reviewing you can look at it and go, this might well work, and at least they've done what they said they were doing, and it may be a good idea, and that you get some public external recognition for that. So I think this is one of the solutions. I think, as I said kind of at the beginning, I think we're being pushed sort of kicking and screaming into the world of open data at some level, and it can't happen fast enough for me, to be honest. I think this is one of the solutions. I would also like the opt-in author list, because you also have the high-risk reward then. If you do something new and controversial that no one under collaboration has got time to review, or no one wants to sign it because it would be really embarrassing if it was wrong, they just don't sign it, and you put a paper out in your own name. And if it's wrong, you go down with the paper. If it's right, you get all the credit because no one else signed it. So that's what I would like to see as well. And the Bell experiment in Japan did run a system like that. And often experiments do run that once they've stopped taking data, but people are still analyzing the data. But I think we should move to that sooner. Sorry, that was a long answer. But,
yeah. Thanks, it was very nice. You do have a kind of monopoly on this type of science, right? So if someone wants to do this type of thing, obviously they have to go to human. That's essentially how you start.
Yeah.
We do have a little bit of that issue in sequencing technology. There's also like one company dominating, and there could be sort of similar things. And do people try to beat against that? But how do you guys make sure that this monopoly is not misused? So do you have some internal control? I mean, you said openness would be one of the ways, right? But then also, I guess maybe if you have 3,000 people, one of them shouts out. But
one of the important things, as I mentioned with CMS at the end, is that the collaborations are independent, and they're independent of Cern as well and of each other.
Okay, so this decoupling of the detector versus the ring, right?
Yeah. So at least it's not single. At least it's not one political control. Cern doesn't have political control on what Atlas and CMS do. It has an influence, has a say, but in the end, it could not suppress a result from Atlas or CMS. Okay, and and Atlas and CMS are in competition at some level with each other. So if one of them messes up, the other one can point it out. So that's part of the answer. It's not a complete answer, but it's an important part. We have a technology problem. In fact, a lot of our technologies, especially the silicon, for instance, if Hamamatsu went bust, we wouldn't be able to build anything, basically. So we have single-point failures in the technology landscape as well, which we try hard to, qualify new companies so that they can build something for us, and then the company decides there's not enough money in it and they walk away. Or it's a continual problem. Sorry.
Okay.
Thank you for all the questions.
Thanks
That's really
ever
good.
so much, John. That was really great. Thanks ever so much.